All right. All right. So I actually sent this to you, and I uploaded it to Blackboard as well. But it's when I saw this, I was actually looking through on the ACS publications website, and they had this molecule of the week, which was is it the week? I think it's molecule of the week, molecule of the month, one of them. But anyway, this croconate violet, and when I was reading it, it talked about the electrons being delocalized. So what that means is that there's constant resonance happening with this molecule. And so we're going to use this as an example of resonance, and we're going to work through it. There are multiple resonance forms that you can draw, and so we're going to do that. It's mostly used for protein staining, but it's like a dye for staining proteins. If you haven't done that in biology yet, you will at some point. And the way you make it is to take malonitrile, which is this compound right here. I forgot to put the nitrogens in my drawing, in my program when I was building these structures. There should be a nitrogen on each end. So malonitrile, and then dipotassium croconate, which is here, right? We're not worried about the reaction right now, but it's this carbon right here that's going to displace each one of these oxygens. But we're not worried about that part. There are a few ways that you can do that, but that's not what I care about. I want to talk about the resonance. So let me copy that. And it gave us some questions down here. Locate all the functional groups and croconate violet. So let's do that real quick. What is this functional group? This functional group, this one, and yeah, that's it. Let's do that. Somebody tell me what the CN is. C triple bond N. So it actually looks like that. Anybody?
Is that an alkene? Alkyne? My bad.
Okay. It would be considered an alkyne if the nitrogen was a carbon. But you're right. Alkynes do have triple bonds. That's absolutely right. But in this case, there's a nitrogen here. And so it changes the functional group. It changes the functionality, the reactivity, everything. We saw it the other day when I think I pulled up Paxlovid, the COVID antiviral, and we talked about it. Let's go back to it, and because that way everybody can get refreshed all at the same time. Let's see. Here, right? So C triple bonded to nitrogen is what we call a nitrile, right? So it's a nitrile. But that's a good educated answer, because you saw that triple bond and you immediately thought alkyne, so that's good. But it's a specific class of functional group called a nitrile. All right, so we're gonna put that in. So that's a nitrile. What about here? Right here. Anybody? You have a carbonyl, which is a generic functional group, but on either side of that carbonyl, you have a carbon. What functional group is that?
Ketone.
Good. It's a ketone. Excellent. And what about the one we have circled here? Everybody should know that one.
Alkene.
It's an alkene. Good. All right. So up here, remember we were talking about, this is a good place to introduce this, or at least talk about it. We were talking about covalent bonds and shared electrons, and I mentioned something about ionic bonds in quotes, but it's not really a bond, it's more like an attraction. This is an example of that right here. This oxygen is negative, the potassium is positive, and so they kind of hang out together, right? Because they're attracted to, each one is attracted to the opposite charge of itself. So potassium being positive is attracted to oxygen. Oxygen being negative is attracted to potassium. Let me fix that. So this is an example of an ionic, I'm gonna put bond in quotes. It's not really a bond. A bond is when electrons are shared. All right, so it's really an electrostatic attraction. So you got two oppositely charged atoms and they hang out with each other. All right. A lot of times when you see something like this, it's also considered, when you have a metal and a non-metal like that, it's a salt. So it'd be a type of potassium salt. All right. Let's get to the resonance part. Uh-oh. So it said, the question asked to draw at least two resonance forms beginning, it tells us where to start, beginning with each oxygen as a donor. So we're going to start, let's start with this oxygen right here. This is my donor. What's the acceptor? Because remember, for resonance, the donor and the acceptor have to be adjacent to one another. So what's the acceptor? Anybody? What do you think? What's connected to that oxygen? Remember, donors are pi bonds and lone pairs, and acceptors are what? Pi bonds and what else? Cations. Good. So what's attached to that oxygen? What's adjacent to it?
The pi bond.
A pi bond. You see that pattern right there, right? Good. Now, in this case, this is an allylic type system, but it also falls into another class of compounds because it's what we call conjugated. So this is where it's conjugated. And for now, the definition of conjugated is just going to be alternating single and double bonds. That's for now. When you get to part 2, that definition is going to become more nuanced. Oh, I can't spell. So the temptation would be to put the pair of electrons on this carbon right here. Right, but we're not going to be able to do that because that carbon has a oxygen on it with a negative charge, and that is not going to be stable, right? But because it's conjugated, we can do something else. We can put that pair of electrons somewhere else because all of these orbitals are overlapping, so they can all share electrons. So we can do this. We're going to put this here and make a pi bond. We're going to take this pi bond and put it here. And then we're going to take this pi bond and turn it into a lone pair. Right? Only because this system is conjugated. Right? Now, if the oxygen on the other side wasn't there, then sure, we could put that pair of electrons right there on that carbon. But because this is conjugated, we can't do that. All right. So what does that new resonance form look like? What does this arrow tell me right here? What's that arrow telling me? You see how I have it? I don't have it on an atom. I have it between the two carbons right here, right? Are y'all following? It's between these two carbons. So what does that mean? Right, if I put the arrow there between those two atoms, what it means is that I'm putting a pi bond there. So that's that, and then I need to break this one. And now there's a lone pair here. Yes or no? Anybody not following? All right, can we do the same thing on the other side?
Yes.
We can. It's the exact, it's the, not, let me take that down some. It's the exact same pattern, isn't it? Right here. Here, here. It's the exact same pattern of conjugation, just like on the other side. Can somebody, for lunch, I'm putting lunch on the line. Can you put the arrows in for that? Annotate the screen and put the arrows in.
How do we do that?
If you're on your laptop, there should be a button up top on the toolbar that says annotate with a little pencil on it. Do you see that?
No.
Hold up, let me change the security options. That's the problem. Because I might have it, it may be turned off since I'm using my live participants to share, unmute, chat, rename. Okay, why can't I do that? Let me change the, maybe change the settings. Man. There should be a way to turn that on. Okay, I said share screen, share whiteboards. Yeah, I don't know. They must have changed something. Because normally you could, if I was on my laptop, I could definitely turn, it would already be turned on. So just tell me what to do and I'll put the arrows in. What would you do?
I can't see your screen anymore.
Oh, hold up. Yeah, it's coming back up. Can you see it now?
Yes.
Okay.
So there'll be a arrow from that oxygen next to the potassium.
You want to put it here, right?
Yes.
Notice again where my arrow stops matters. I'm putting it between the carbon and the oxygen. So what that means is that in the resonance form, I'm going to have a pi bond there. So now this carbon right here is unhappy unless I do something else, right? So what else am I doing?
From that carbon to the wait. That carbon to y'all put to the next carbon from the pi bond to the carbon?
right here. I'm saying
Yeah.
that to
Yeah,
put a pi bond. So that's gonna shift the pi bond between these two atoms.
and then from that carbon to the NC.
To the carbon right here, right?
Yeah,
Okay, right. So and this is for thank you for that too. And I owe you lunch. You're gonna you can put your Cash App in the chat. For everybody, where my arrow stops and starts matters, right? So if I start the arrow here at the pi bond, for instance, and I move it here between the atoms, that means it's becoming a pi bond. It's not becoming a pair of electrons. If I start the arrow here on the pi bond and I move it to the atom, because I'm moving it to this carbon right here, then that means that that's going to become a lone pair, right? And that does matter. You'll see this later, but I'm just trying to reinforce it now. So when you see it again, you'll have some familiarity with it. So this is
Couldn't
going
you
to,
use the other O though?
we already did. We used that one with the other resonance form.
Oh, so you're just showing us a different.
Because both of those oxygens can do resonance. They're just going to do it. And both of them are going to follow the same pattern, but the resonance form for this one, you'll see, is going to be, I'm actually going to just steal this. Let me see if I can steal it. Nope. I'll just redraw it. So that this resonance form now is going to have, instead of a pi bond on the right side like I had over here, the pi bond is actually going to be here on this side. And this oxygen is going to have a double bond to it and not this one. You see what I'm saying?
So if this was on like the test or whatever, either way would be correct. We could either go from the left or from the right.
Yes, because if let's go back up to the question. The question said to draw at least two resonance forms beginning with each oxygen as a donor. So we started with one, and then we're showing now the second resonance form with the other oxygen. So to answer that question with a short answer, yes, both are correct. All right. Questions about that? This is a little bit more complicated because the system is conjugated, right? It's got that extended pi system, and so the resonance is going to be different. We're going to look at some examples like that too in a minute. But I promise you, if you master resonance, arrow pushing, part 2 is going to be half of the battle of part 2 is already won of this class. If you understand resonance, and when we get to the nucleophiles and electrophiles, if you understand how to push arrows, half of the battle, I'm spending a lot of time in part 2 reteaching part 1 right now this semester, because a lot of students just didn't grasp what was being taught in part 1, or they forgot it. They may have grasped it when they were in the class, but they forgot it. But if you can master arrow pushing and resonance, you're going to be, part 2 is going to be infinitely easier. All right. So questions? Any questions about this example? All right. So now it says, the third question, draw at least 2 resonance forms beginning with the alkene adjacent to the ketone as the donor, because we know that pi bonds can be both donors and acceptors. So let's work those out. Let's see what we can do. Let me just erase all that. All right. So we're going to start here with this as my donor, right? And then connected to that is this ketone. So that's the pattern. And it's similar to an allylic system in that you have your donor here. And then this third atom is the acceptor. So it still falls into that category or the pattern of an allylic system. And actually, what's the charge on that carbon in the carbonyl? I'm feeling generous today. I may buy a second person lunch too. Tell me what the charge is on that carbon and tell me why it's that charge. This is a kind of a nuanced question, but I want to see how you're thinking. Why would that carbon be considered an acceptor?
So there's a positive charge?
Say that again. Positive.
Yes.
Okay, good. Why does it have? You're right. Right now it's neutral, but it's a high partial positive. So I agree with that. Why?
We're talking about the carbon connected, double
The
bonded
carbonyl.
to. Oh, okay.
Mm-hmm. You're right. It is partially positive, highly partially positive. But now you got to tell me why. So the carbon right.
Because it's yes.
Mm-hmm.
Okay. Because it will be the carbons will, like the electrons, will be more attracted to the oxygen because
Come
of
on.
electronegativity.
Come on. When you just earned yourself a nice little lunch today. That's exactly right. The carbonyl has a dipole, a huge dipole towards oxygen. So that makes this carbon. That's excellent answer, by the way. Thank you for that. Who was that? I couldn't see. So you got to tell me who you are.
John Adams.
Nice work. Just put your cash out in the chat. So the carbon is partially positive because of the bond to oxygen, which is a highly polarized bond, right? And then oxygen is partially negative. So that's why that's the acceptor. And that's why we can liken this to an allylic cation. It's just the exact same type of system. So if it's an allylic cation, how do we draw the resonance form for that? Anybody remember? I gave you 3 allylic systems, an anion, a cation, and a radical. So it falls into the category of an allylic cation. Tell me what you would do. Even if you have to go back in your notes,
What
that's
I
no
would do
shame in
is
that.
I would move.
Go
Okay.
ahead.
So you're asking where I would move the electrons?
So this is my donor. Remember, we
Right.
already established that the carbonyl is the acceptor, the carbonyl carbon. So that makes this the donor, right?
Right.
So so now we know what the donor acceptor is. We know the pattern is like an allylic cation. So what do we do with that?
Will we move the electrons to make a pi bond on the
Here?
yes, right there. Yes.
Good, excellent. And then now, if we make a pi bond there, we understand this too. That carbon can only have 4 bonds to it. And right now, if I left it, it will have 5. So what do I have to do in addition? Because this is not a typical allylic cation, right? It's got a carbonyl. So what do I need to do there? I need to do one other thing. But you're absolutely right. We're going to put a pi bond here.
Here on top. Okay.
And then I need to take the pi bond here and do what? I got to break it and give it to oxygen. Is that right?
So, yes.
Because otherwise that carbon that I have circled in, well, I got 3 of them circled in black. The carbon here will have too many bonds to it. So anytime I move a pi bond like I'm doing here, I'm moving it to a carbon that already has a pi bond, then that other pi bond is gonna have to break. Right. So then now I can draw the resonance form here. This is O minus, a double bond is here. And this is CN, this doesn't change. There's one other thing we have to take into account too, but I'll ask that question in a minute. All right, am I missing anything? That's a loaded question, by the way. I am missing something. I just want to see if you catch it. Right, so this is where my new pi bond ends up. What about this carbon right here? What's the charge on it?
It has a positive charge.
Excellent, excellent, excellent. It's got a plus charge on it. Anytime I break a bond to carbon and I don't add something else in, a pair of electrons in, that carbon is going to become positive. Right? So now that's on the right side. Can we do the same thing on the left? With this system over here. Is that right? Can't we do the same thing there?
Yes.
We can. So I want you to work on that. Come on. All right, I want you to work on drawing that other resonance form, just like we did the one on the right. You got the pattern, you got the arrows. You're just gonna do those, put those same arrows on the other side. Right, and again, notice where my arrows start, where they stop. Right, if I'm breaking the pi bond between these 2 carbons right here, right, I start the arrow in the middle of the pi bond. If I'm breaking this pi bond from between carbon and oxygen, I start the arrow in the middle of that pi bond. That all of those little technicalities, they matter, because that's how you tell with those arrows, you're telling where my electrons are coming from, where they're going to. And if your arrow is at Piggly Wiggly, but the electrons are at the Russell store, then you got a problem. So it's very technical and it's very nuanced. So we're going to get that part together, like before we, get into more complicated stuff and we don't have the conventions down, the basic stuff down. All right. Any questions about these examples? I thought this was like really cool when I saw it. So I was like, we gotta touch that in class. All right, let's go back to our examples that we're working through. And let's look at, we did B already, I think. Let's do, I want to do one where it's extended. You pick one, y'all pick one. Out of this, we're gonna do one more out of 1-36. We're gonna do one more. So somebody pick one.
F.
F, okay. All right, let's do that. We can actually do this right here. We don't even have to copy it and paste it. All right, we got a pair of electrons here, one there. So this is an example of that 4th type of system I told you about. It's like a diatomic system where the donor and acceptor are immediately adjacent. Which one is the donor? What do you think? Donors again, lone pairs, pi bonds. Acceptors, pi bonds, cations. Which one is the donor?
The oxygen.
Oxygen. That makes the carbon by default and the acceptor, but you can see that it's an acceptor because it has a plus charge on it. So I want to go from here to here. How would I do that? Man, I wish I could annotate that screen. Normally, if we were in class, I would have people coming to the board and stuff, but that's all right. We're gonna get it right. How would you show it? Going from the structure on the left to the structure on the right. Look at what chain.
You would go from the O and do an arrow to that first line to make it a pi bond.
Right here.
Mm-hmm.
Yes, that's exactly right. And that would indicate that I'm taking that lone pair and using that lone pair to make a pi bond between carbon and oxygen. Somebody help me with the charge on carbon. How would you calculate that? We talked about formal charge already. I just need to like keep you aware that this stuff pops up all the time. So you need to know how to be able to calculate a formal charge. No matter, even though we passed that section, you're always going to see it. So you need to have that skill set. How do you calculate that plus charge on carbon? Anybody?
You take the valence and then you subtract that from the number of bonds or the number of regions it has.
Okay, good. So we had the valence for carbon is 4, and the actual what's around it is half of each bond, right? So 1 electron from each bond. It's got 3 bonds to it, so it's 4 minus 3. So that's +1. What about oxygen? How did we calculate that? We know the valence is 6 for oxygen. What's around it? You got a lone pair, that's 2. You have a pi bond, 1 from each, 1 from the sigma, 1 from the pi. Well, you have a double bond, but you have 1 electron from each one of those, so that's 4. And then 1 from that bond is 5. Right, so 6 minus 5 is also +1. And if you notice in your resonance forms, they have the same charge. That's actually, I used to teach this like going rule by rule, but now I don't. I just, when we encounter something, I explain it. But those resonance forms have to have the same charge overall, the same total charge. All right, I think I want to do one more because this will drive home the point that we just looked at with that croconate structure. How do we go from the structure on the left to the structure on the right? Look at what changed. What changed in that structure on the right?
So basically the pi bond transferred to the carbon.
Okay, so the pi bond got shifted over.
Right, to the right.
Mm-hmm. So like that, is that right? Isn't that what happened?
Well, yes, that's what I'm talking about.
Mm-hmm.
And then the pi bond that's connecting the oxygen, yes, went up.
Just okay, yeah, you're right. Here, we broke that pi bond, yes. And if you look at this structure, I don't like when it's written out linear like that, but this is the exact same pattern we just saw down with that croconate, right? Where we did this and then that, because again, the pi bond is the donor in this case, and then the carbonyl carbon is the acceptor because it's partially positive. It's the exact same thing. All right, let's go down to here to 137, and hopefully you got some scratch paper because we're gonna work through we're gonna take B. Well, actually, let me just cut this and put it on a blank piece. But if you look at the question, it says draw the important resonance forms to show delocalization, which means what? What does that term mean again, delocalization? We talked about that the other day. Anybody help me out? What does it mean to delocalize electrons? Too quiet.
So it's like they're not, like they don't have a bond. So like to remove them from the bond.
Actually, okay, let me ask you this. So if you had a 100-pound boulder that you were holding and you were sitting next to a person on your left and a person on your right, and you had a chance to pass it to one of them, would you do it?
Yes.
You would. That's all it is. So when we delocalize electrons, we're taking them from one location in an atom, in a molecule, and if it's possible, meaning if you have an acceptor adjacent, we're passing it to the acceptor. And we keep doing that as many times as possible so that you can have as many resonance forms as possible, right? So that the charge is as stable as everything in chemistry happens for stability, right? You're trying to go from a less stable state to a more stable state. That's everything in the universe. It operates on that principle, going from less stable to more stable. All right, we're going to take, let's start out light. Let's take A. Well, that'll be a little appetizer. And then we're going to do, so we'll do A. We'll do E, because that's really important. We're going to do C and H. All right. So let's start out with A. And we're going to, so that's CH3, C double bond O, CH2 minus. What type of system is this? Number one. Number two, how do we push the electrons to generate the resonance form? So what type of system does this fall into? And number three, where's the donor and where's the acceptor? That should actually be number two. So system, identify the system, identify the donor and the acceptor, and then put the arrows in to generate the resonance form. So what type of system does this fall under? It's got a negative charge, so that means it's a what? An anion or a cation?
Yeah, that's the anion.
Anion, good. All right, it's got a negatively charged carbon connected to a pi bond or a pi system. So this is an allylic what? Anion, is that right? We know this system because we saw it already. And it has a specific way to move those electrons and it never changes. You can have the largest allylic system in the world and it's going to follow the exact same pattern every single time. So where am I going to start? Which one of these is going to be my donor?
The carbon.
The carbon with the lone pair. And this is, excuse me, this is the acceptor. All right.
I have a question.
Go right ahead.
Could you explain why the carbon would be the donor? I know it has the electron pair, but could you explain why the oxygen is the acceptor, even though it has a higher electronegativity?
Well, that's you just answered it, right? It wants more electrons because it's more electronegative, but it's not necessarily the oxygen that's the acceptor. It's we just showed down it on the other example that this carbon is,
Oh, it's the other
Uh,
carbon.
it's the carbon that's going to take the electrons, and by default, we're going to push the pi bond to oxygen because it's more electronegative, and to keep carbon with the octet, right? Because otherwise, if we don't break that pi bond, it's going to have 10 electrons around it. If that
Okay,
makes
yes,
sense.
I understand.
Mhm. That's a
Thank
good
you.
question. Very good question. Very thoughtful question. So what are the arrows for the allylic anion pattern? What are we doing? Where do we start? We always start at the donor, is that right?
Yes.
So we're going to start here like that, put it between. So what that tells us that we're making a pi bond there, and then we want to break the pi bond to oxygen. This is a nice clean example. Is that right? And
Yes.
then what's the charge on each one? Both of them have an overall charge of -1. That's again, that's a rule for resonance, that your resonance forms have to have the same charge. So if you did this example and you didn't have a negative charge in your other resonance form, then you know something was wrong. All right. Let's do we got 3 minutes left. Let's do E. E is a good one because it's an extended example. I'm gonna turn it though. It's not as hard as it looks. It's actually fairly easy when you think about, once you identify the pattern, right? So here, what pattern does that fall into? It's got a negative charge atom on one end, and that atom is connected to a pi system.
Allylic anion.
It is. And once we know that, then what else do we know? How the electrons move. This is the donor, the pi bond is the acceptor. So we know now how to push the electrons. We're going to do this and that. Are we following? Anybody not see that? Notice I didn't touch the other two pi bonds yet. Can I do that again? Do we see the same pattern again? That's the exact same pattern, am I right? You got a negatively charged atom that's bonded to a pi bond directly, right? So I can do this. I can do this again, where I put those electrons there, put those here. Is that right? Anybody not seeing it, or you stuck? Or you have a question, but you are afraid to ask it. Don't be afraid to ask it. Is that right?
Yes, I think that's correct.
Okay. Do you see the pattern again?
Yes, I see it.
So what does that mean? It means we can do it again, right? We can take
Yes.
the pair of electrons and push them here to make that a pi bond, and then take this and put them on that carbon right there.
I have a question.
Go right ahead.
So, since there's a pattern, you could do that for any molecule,
Yes.
like you can continue to move it around
Mhm.
in the end, does it matter where you placed it?
Well, it matters from the sense of where the atoms are, but it doesn't matter in the sense of how many resonance forms you can draw. I had a little system that I used to use where if you add up the donors and the acceptors, you can figure out like how many total resonance. I always get this question, how many total resonance forms? In this case, you got 1 donor and 3 acceptors. And so you're gonna have it at minimum, you're gonna have 4 resonance forms, right? But that's a,
Will
ahead.
there be like questions where it'll say like, show me 3 resonance forms of
Yeah,
this molecule, or?
yes. Yep, you will see that. Questions like that. We can do this again too. Right here, right? We can do the same thing here. And we go back to, we'll get to another structure that looks like this. But now if you notice from the first structure where we started to here, when you compare them, the double bonds have been shifted around. Do you see that?
Yes, so essentially you can come back to the original form.
And go, exactly. That's why we use double-sided arrows like that. You can go from, all these are interchangeable. And the more of them you draw, the more stable that negative charge is. And that's the whole purpose of doing it, delocalizing that charge over as many atoms as possible, right? So this is a very stable anion, because I mean, you can see you have 4 resonance forms that you can interconvert between, and they're all equally valid in this case. Sometimes you'll have a situation where you have resonance forms that are not, they don't contribute very much because they have too much charge, or they might have the overall like structure compared to the original might be, you know, it might not be palatable. But yeah, the more resonance forms you can draw, the more you can delocalize the electrons, the better, because it's going to increase the stability. All right. Other questions? We got to stop. I'm 4 minutes over. My apologies. We'll finish this up on Friday. We're gonna finish these, and I may even break y'all out to work on some of these examples on this page right here. We'll have a warm up, a little warm up Friday with 140. So if you want to start playing around with those, you can. And don't forget, I forgot who that was. It was like 2 people who I owe lunch. So make sure your name is in the chat. Your Cash App name is in the chat, so I can make good on my promise.
Have a good one.
All right, y'all take care. See you Friday, God willing.
Bye, have a nice day.
Okay, take
Dr.
care.
Russell, I have a quick question.
Go ahead.
You're saying that we're gonna work some more on this worksheet on Friday, but I thought we had that exam on Friday.
We do. The
So
exam
we're
is
gonna
going
do
to be,
both?
no, the exam is on Blackboard. It's open notes. You'll take it over the weekend.
Okay, I just wanted to make sure.
Yeah, we're gonna keep rolling, and then you can take the exam at any time between Friday and Sunday.
Okay, thank you. Have a good day.
Okay, you too. Take care.